Hello, this podcast is on conservation of momentum in collisions and explosions. First, we'll take a look at why Newton's laws of motion dictate that momentum is conserved. We'll explore elastic collisions, perfectly inelastic collisions, and explosions, as well as two-dimensional collisions, and how conservation of momentum is an important governing equation in analyzing these events. Newton's third law dictates that momentum is conserved during collisions in the absence of an external net force. And let's take a look at this proof. Let's have a two-object system, and in that case, the momentum of the system is equal to the momentum of particle 1 plus the momentum of particle 2, and the change in the momentum of the system is equal to the change in the momentum of particle 1 plus the change of the momentum in particle 2. We learned from a previous podcast that in general, the change in a particle's momentum is equal to the force applied over a period of time. And for all forces, whether they're constant or varying, this can be represented by the integral of F dt evaluated over the time period the force was applied. So we can go ahead and make this substitution, and we come up with our equations for the change in the two particles' momentums. And Newton's third law tells us that these forces in these two equations are equal to each other, but in opposite directions. So we make that substitution, and we find out that the change in particle 1's momentum is equal to the change in particle 2's momentum, and therefore the change in the system's momentum is 0. Let's look at an example of this. So we have a 100-kilogram running back moving at 8 meters per second. He collides head-on with a 120-kilogram linebacker moving in the opposite direction at 5 meters per second. After the collision, the two players bounce off each other. The running back has a final velocity of 2 meters per second in the opposite direction. In other words, they bounced back after the collision. What is the linebacker's final velocity? Since momentum is conserved, we know that the initial momentum of the running back and the linebacker are equal to the system's final momentum. And so we can set up this equation, we're treating this as a two-particle system. We've got the running back and the linebacker initial momentums, the running back and the linebacker, the final momentums. Notice that we know all the variables in this equation except the linebacker's final velocity. So we can go ahead and rearrange this to solve for the final linebacker's velocity, plug in our numbers, and we find out that the linebacker is moving at 3.3 meters per second. Now keep in mind the linebacker was originally moving at -5 meters per second, so the linebacker also bounced backwards after this collision. Let's explore two different types of collisions. The first one, elastic collisions. This is when two or more objects collide and no energy is transferred to thermal energy by way of friction. No energy is transferred to elastic potential by way of deformation of objects, and no energy is transferred to rotational kinetic energy via spinning. In these instances, kinetic energy is conserved as well as linear momentum, so this gives us a second governing equation with which to analyze the collisions. However, most collisions are not elastic, especially on a macro level. If we get to the micro level, such as gas molecules colliding with container walls, these tend to be nearly elastic. Also, billiard balls colliding with each other are nearly elastic. So let's look at analyzing elastic collisions. The following equations are used. We have our conservation of kinetic energy equation, and we have our conservation of momentum equation, where we've substituted in the mass times velocity products in place of momentum. Solving these equations simultaneously gives us the relationship between the final and initial velocities of the particles involved in the collision. So let's look how we do this. First, we're going to take equation 1, and we're just going to multiply it by 2 to get rid of these 1/2, and that leaves us with this. Then we're going to go ahead and separate object 1 and object 2 quantities on opposite sides of the equal sign, and we're left with what I'm calling equation 3. And notice we have the particle 2 on the right-hand side and particle 1 on the left-hand side. We see here that we have a polynomial expression, second order polynomial expression. So I'm going to go ahead and factor these two polynomials. That gives me this, and we'll see in a moment why this is an important step. Moving on, we're going to go to equation 2, which is our linear momentum conservation equation. And similarly, we're going to take objects 1 and object 2 and separate them on the left and right hand side of the equal sign. Then we're going to take equation 3 from the previous slide and divide it by this new equation, number 4. And you can see when we do that, the masses cancel out and the velocity initial minus velocity final terms cancel out, and we're left with the initial velocity of object 1 plus the final velocity of object 1 is equal to the initial velocity of object 2 plus the final velocity of object 2. Or we can rearrange this to get a term that we call relative speed, and we can see that the initial relative speed is the velocity of object 1 minus the velocity of object 2, and the final relative speed is negative the final velocity of 1 minus the final velocity of 2. What this leaves us with is the general conclusion that the relative speed of two objects after the elastic collision is the same as before the collision, but these relative speeds are in the opposite direction. So let's move on and look at an example. Object A is moving at 5 meters per second when it collides with object B, which is moving at 2 meters per second in the opposite direction. So we want to calculate the relative speed before the collision. That's the initial velocity of object 1 minus the initial velocity of object 2, and that gives us 7 meters per second. Well, from our previous proof, we see that after the collision, the relative speeds need to be the same magnitude but in the opposite direction. It's important to note that we can't tell the individual velocities after the collisions unless we know the mass of each object. Now, we can go ahead and do that, but solving elastic collision problems involves cumbersome and time-consuming solving of simultaneous equations. However, there are 3 limiting cases we can solve, and let's take a look at them. First, we have identical masses of the two colliding objects. For example, 2 bowling balls, each with a mass of 4 kilograms, collide head-on with each other. Ball 1 has an initial velocity of 2 meters per second, and ball 2 has an initial velocity of 4 meters per second in the opposite direction. What are the two velocities of the bowling balls right after they collide? We have 2 unknowns, the final velocities of ball 1 and ball 2, so we need to use 2 equations, the conservation of momentum equation and our relative speed equation, to solve this problem. First, we're going to work with our conservation of momentum equation. So we go ahead and plug in our masses and our initial velocities. We don't know the final velocities, but we do know the mass after the collision. We go ahead and solve this equation, and we find that the final velocities added together have to equal -2. We're just going to go ahead and rearrange this to solve for the final velocity of ball 2, and that leaves us with this expression, which I'm calling equation 1. Next, we want to take equation 1 and sub it into our relative speed equation, which is this. And when we go ahead and do that and do all the number crunching, we find that v sub 1f is equal to -4 meters per second, so that's the final velocity of ball 1. Then we can sub this back into equation 1 up here to find the final velocity of ball 2, and we find that it is 2 meters per second. This leads us to the solution for our first limiting case. When the masses of the two objects are identical in an elastic collision, they will swap their velocities. So in other words, the initial velocity of the first object will be the final velocity of the second object, and vice versa. Let's move on to our second case. In our second case, a much heavier object is running into a much lighter object at rest. So in this case, m1 is much greater than m2. So we want to use our 2 conservation equations. And we have the kinetic energy conservation equation and the momentum conservation equation. Because object 2 is initially at rest, these velocities are 0. If we solve equation 2 for the final velocity of object 1, the heavier object, we wind up with this expression. Notice this ratio, the mass of object 2 divided by the mass of object 1. Well, since the mass of object 2 is much smaller than the mass of object 1, this ratio is essentially 0, and that tells us that the final velocity of object 1, the heavier object, is approximately equal to, or essentially equal to, the initial velocity of object 1. Next, we know that the relative speeds before and after the collision are equal and opposite. We can use our relative speeds equation, and we know that the initial velocity of object 2 is 0. We also know the final velocity of object 1 is equal to its initial velocity. We can also make that substitution. We wind up with finding out that the lighter object's final velocity is equal to twice the heavier object's initial velocity. Therefore, for our second limiting case, when a much heavier object runs into a stationary lighter object, the velocity of the much heavier object is unchanged, while the lighter object moves twice as fast as the heavier object after the collision. Please note, in this instance, both objects are moving in the same direction, which will be the direction that the heavier object was originally moving. Let's look at our third and final limiting case. In this case, a much heavier object is at rest and a much lighter object collides with it. We need to rearrange our conservation of momentum equation to solve for the final velocity of object 2, the much heavier object. Initially, the heavier object, object 2, was at rest, so this velocity is 0. We can go ahead and rearrange and solve for the final velocity of the heavier object. Notice we have this ratio, the mass of object 1 over the mass of object 2. In this limiting case, m1 is much smaller than m2, so this ratio is essentially 0. And that leaves us with the heavier object, which was initially at rest, remains at rest. Now we want to sub this into our equation 3 from case number 2, which is simply our relative speeds equation. And so the initial velocity of object 2 was 0. We now know that the final velocity of object 2 is 0, and we can solve this equation, and we find out that the lighter moving object's final velocity is equal in magnitude to its initial velocity, but in the opposite direction. Therefore, in our third and final limiting case, when we have a much lighter object running into a heavier object at rest, the lighter object maintains its original speed but in the opposite direction, and the heavier object remains at rest. Let's move on and explore perfectly inelastic collisions. A perfectly inelastic collision is when two objects collide and become entangled and move as one after the collision. Kinetic energy is transferred to thermal energy because of friction, and elastic potential energy because the objects deform. Therefore, kinetic energy is not conserved, and only momentum is conserved during this collision. We need to solve problems using the conservation of momentum equation. So here it's set up in its basic form for a two-particle system. Since the objects stick together after the collision, the final velocity of object 1 is equal to the final velocity of object 2, and we can make that substitution into this equation here, and we wind up with this conservation of momentum equation. And its more useful form is this. The final velocity is equal to the initial system momentum divided by the total mass of the system. Now, sometimes in the problem you'll be asked to find the initial velocity of an object, and if you do that, you just take this equation up here and rearrange it for one of the initial velocities. Let's analyze an example. We have a 100-kilogram running back moving at 8 meters per second, and he's tackled head-on by a 120-kilogram linebacker moving at 5 meters per second in the opposite direction. They become entangled and move as one after the collision. What's their final velocity? So we go ahead and take our formula from the previous screen, which is already set up for final velocity, and we plug in our mass and velocity values, and we find out that they're entangled bodies move at 0.91 meters per second in the positive direction. And we said that the running back was moving in the positive direction at 8 meters per second. So after this collision, the running back is still moving forward, but the linebacker is moving backwards. Let's move on and look at explosions. An explosion is where one object explodes into more than one object whose total mass remains the same. The initial object may be at rest or it can be moving. Total momentum is conserved in explosions, but kinetic energy is not. So we're left with our conservation of momentum equation to analyze these problems. The initial system mass, capital M, times v sub I, its initial velocity, is the initial momentum of the system. The final momentum of the system is going to be the sum of all the individual parts' momentums. So that's m1 times v1 plus m2 times v2, and so on for however many particles you have after the explosion. For an explosion that creates two objects, our equation is the system mass times the initial system velocity is equal to the momentum of particle 1 plus the momentum of particle 2. If the original object is at rest, then the left-hand side of the equation becomes 0, no momentum, and we can rearrange this and find out that m1v1, the momentum of particle 1, is equal to the momentum of particle 2, but in the opposite direction. Let's look at an example. A 100 kilogram mass at rest explodes into two pieces, one 20 kilogram piece and one 80 kilogram piece. If the smaller piece is moving at negative 20 meters per second, what is the velocity of the larger piece? Using our conservation of momentum equation, we have the initial momentum of the system, which is 0 because it's at rest, is equal to the momentum after the explosion of the individual particles. And of course, we know everything in this equation except for the velocity of the second particle. We can rearrange this, plug in our numbers, and we find out that the heavier piece, piece number 2, is moving with a velocity of 5 meters per second in the positive direction, which is opposite of the direction the smaller piece was moving. Let's look at some general conclusions we can draw from this example. The speeds are inversely proportional to the particles' masses. In other words, the heavier object is 4 times heavier than the lighter object, so its speed will be 1/4 that of the lighter object, and the objects will be moving in opposite directions. Let's move on and look at an example where the particle is moving at the time of explosion. So in this example, it's the same particle as the previous slide, except it's moving in the positive direction at 2 meters per second at the time of the explosion. After the explosion, the smaller 20 kilogram piece is moving in the negative direction at 20 meters per second, and we're asked to find the velocity of the larger 80 kilogram piece. We need to use our conservation of momentum equation, just like before. So we go ahead and plug in our numbers. We know everything except the final velocity of object 2 after the explosion. So we can rearrange this and solve for the velocity, and we find that the heavier particle is moving 7.5 meters per second in the positive direction, which is the same direction the original particle was moving before it exploded. Moving on to our final topic, let's explore two-dimensional collisions. Momentum is a vector quantity, so momentum in both dimensions must be conserved during a collision. Therefore, when we go ahead and analyze momentum in two dimensions, we're going to use the same vector analysis equations and techniques that we've used to analyze two-dimensional motion and two-dimensional forces. So here are our two equations, conservation of momentum in the x dimension and conservation of momentum in the y direction. Let me stop and talk about three-dimensional collisions. We would treat this the same way we are two-dimensional collisions, except we would have a third dimension and we would have to find the momentum in the z dimension, and of course that would also be conserved. Back to our two-dimensional situation, let's consider a glancing collision, and that's where two objects collide but not directly head-on. And that would look something like this. And in this case, we have object 2, which is initially stationary, and we have object 1 which is moving into it. So if you've ever played pool or billiards, this would be a case of the cue ball running into a stationary ball. We know from experience that the one ball goes down and to the right and the other ball goes up and to the right. What we need to recognize here is that the initial momentum of the system is horizontal in the x dimension, and therefore when we add up the momentums of the two individual balls after the collision, their momentums have to add up so that the total system momentum is also along the x-axis. So we can go ahead and take our conservation equations for both dimensions, and we can take m1 v sub 1 f times cosine theta plus m2 v sub 2 f cosine phi. So theta is the angle above the x-axis that ball 1 moves in, and phi is the angle below the x-axis that ball number 2 moves in. And so we're just using our vector analysis equations to come up with the x component of velocity 2 after the collision and the x component of velocity 1 after the collision. We'll do the same thing for the y dimension, only we use the sine of theta and the sine of phi instead of cosine. If the collision is elastic, we can also use the conservation of kinetic energy equation, and this is it. Keep in mind that kinetic energy is not a vector quantity, so this is the equation we use. We do not break kinetic energy into the x and y dimension because it's not a vector quantity. If the collision is inelastic, we cannot use this equation to help solve our problems. Let's analyze a real-life situation. A 1,500 kilogram car traveling north at 15 meters per second drives through a stop sign at an intersection and collides with a 2,500 kilogram SUV traveling east at 20 meters per second. The two vehicles become entangled and move as one after the collision. What is their speed and direction? And we'll find the direction as an angle theta measured from the positive x-axis counterclockwise. This is a perfectly inelastic collision, so we do not have use of the conservation of kinetic energy. However, momentum is still conserved. So we look at both dimensions, starting with the x dimension. We have our initial system momentum. Notice that the car traveling north does not make a contribution to the initial momentum in the x dimension because it's traveling due north. And our final momentum after the collision in the x dimension is equal to the final velocity in the x dimension times the system mass. So we can go ahead and rearrange this to find the final velocity after the collision in the x dimension, and we come up with 12.5 meters per second. Similarly, we can use the y dimension conservation of momentum. Notice that the heavier SUV makes no contribution to the system momentum before the collision because it is moving due east. Our final momentum in the y dimension after the collision is the final y velocity times the system mass. We can rearrange that equation to solve for the final velocity in the y dimension, and we're left with 5.63 meters per second. So now we have our x and y velocities. If we were asked to give a unit vector, we would simply give it as 12.5 meters per second times I plus 5.63 meters per second times j. However, we're asked to come up with the magnitude, speed, and the direction theta. So we use our vector analysis equations. The Pythagorean theorem will give us speed of 13.7 meters per second. And we'll use our inverse tangent function to find that the angle theta is 24.2 degrees north of east. Let's move on and look at an example of an elastic collision. We have an 8 kilogram bowling ball moving at 5 meters per second, and it strikes a stationary 1.5 kilogram pin. The ball is deflected to the left 10 degrees. What are the final velocities of the ball and pin and the pin's angle of deflection? We're assuming this is an elastic collision. Therefore, we know both momentum and kinetic energy are conserved. So we're going to use the conservation of momentum equation to find the angle of deflection and the velocity of the bowling ball after the collision, v sub bf, but we're only going to be able to find that in terms of or relative to velocity of the pin after the collision. So initially, before the collision, our system momentum is 40 kilograms meters per second in this direction, which we might call north. So our final velocity in the y dimension also needs to be 40 kilograms meters per second heading north, or 90 degrees. The initial momentum of the system in the x dimension is 0, and that's because the bowling ball was initially moving along the y-axis. Therefore, after the collision, the final momentum in the x dimension also needs to be 0. So that means that the momentum of the bowling ball after the collision in the x dimension has to be equal, but in the opposite direction of the final momentum of the pin after the collision. So let's take a look at our x dimension equation first and do some more analysis with this. And we see that the final momentum in the x dimension has to be equal to the x components of the ball's momentum and the pin's momentum. So it's the mass times the ball's final velocity times the sine of theta plus the mass of the pin times the total final velocity of the pin times the sine of phi. Now, you may be saying, wait a minute, normally for the x dimension we're using the cosine function and not the sine function. And that's true, but let's notice how we're measuring these angles. These angles are measured from the y-axis, not from the x-axis. So that's why we want the sine of theta and the sine of phi to give us the x component of velocity for both the ball and the pin. We plug in numbers for the quantities we know. We rearrange the equation to solve for the final velocity of the bowling ball, and we're left with it equaling to negative 1.08 times the final velocity of the pin times the sine of phi, which is the angle of deflection of the pin. We still have 3 unknowns in this equation, so we have more work to do. Let's now take our conservation of momentum equation for the y dimension and expand on that. So we know that the final momentum of the bowling ball in the y dimension plus the final momentum of the pin in the y dimension has to be equal to 40 units. We can go ahead and plug in the numbers for the quantities we know and rearrange the equation to find the final velocity of the bowling ball. And that's equal to 0.19 times the velocity of the pin times the angle of deflection cosine phi. We can substitute equation 1 into equation 2, and we get this equation, which I'm going to call equation 3. We can rearrange this, and we come up with the sine of phi over the cosine of phi is equal to negative 1.76, and of course this is just the tangent of phi. So we want to take the inverse tangent of negative 1.76, and we find out that the angle of deflection for the pin is negative 60.4 degrees. The negative just means that we're measuring clockwise from the y-axis. Now we have phi figured out, the angle of deflection. However, we still need to find out the final velocity of the pin and the bowling ball. So I'm going to bring equation 3 up here from the previous slide. We're going to use that in conjunction with the conservation of kinetic energy to find these final velocities. We can calculate the initial kinetic energy because the pin is stationary and contributes nothing to the system's kinetic energy before the collision, and we know the mass and velocity of the bowling ball before the collision. And heading into the collision, the system has 100 joules of kinetic energy. Therefore, our final kinetic energy also needs to be 100 joules, and that is equal to this expression, which I'm calling equation 4. If we take equation 3 and substitute it into equation 4, we wind up with this expression. If we do some collecting of terms, we wind up with the final velocity of the pin is equal to 4.83 meters per second. This is the total velocity of the pin after the collision. We can take that velocity and substitute it up in equation 3 and come up with the final total velocity for the bowling ball, and that is 4.54 meters per second. This wraps up our discussion of two-dimensional motion, which is the final concept for this podcast. Let's summarize what we learned. First, momentum is a conserved quantity. Conservation of momentum is one of the most important governing laws in mechanics. Momentum is conserved in all collisions and explosions. Kinetic energy is conserved in elastic collisions, however it is not conserved in inelastic collisions or explosions. It is cumbersome and time-consuming to solve elastic collision problems. However, we did look at 3 limiting cases of elastic collisions. In the first case of equal masses, we found that the objects swapped velocities from initial to final. So object 1's initial velocity would be object 2's final velocity, and vice versa. In the second case, we had a moving mass that was much heavier than the resting mass, and we found out that after the collision, the heavier mass's velocity was unchanged, and the lighter mass moved with double the heavier mass's initial velocity. And in the third case, we had a much lighter moving mass collide with a much heavier resting mass, and in that case we found that the resting mass did not move at all, and after the collision the lighter mass bounced backwards in the opposite direction with the same magnitude of velocity. We also found that particles move as one after a perfect inelastic collision, and particles move as one before an explosion. And finally, in two-dimensional and three-dimensional collisions, we found out that momentum is conserved in each dimension. Well, this wraps up what we've learned. I hope you found this podcast helpful, and have a good day.